All right, welcome back. Let's take another look at an example of an accumulation function. Because again, what we're doing here is getting you ready to talk about a big result called the first fundamental theorem of calculus. But we need to understand really well what it means or what an accumulation function is before we can tackle the first fundamental theorem of calculus. So I want to start with another accumulation function. Now, the last one we did was a graphical based. This one we're not going to use a graph for. We'll definitely look at some graphs, but we're not going to get our solutions from a graph because, well, this has kind of a weird graph, okay? In fact, I mean, I don't know what it looks like off the top of my head. It's sine squared times 4, and it's a composite and stuff, so it definitely doesn't have just a routine graph that you should know from trig class. But remember what it means to be an accumulation function. So we're going to basically start at 0 as our fixed value, and we're going to accumulate area as we march to the right on the x-axis for these different, what about, I guess, 8 or so different values of x. So we're gonna evaluate 8 different values, looks like, but we could do this for any number of values as we march from 0. I suppose we could go left, but we're gonna go right here to look at the first the values between 0 and 2 pi. Okay, so let's see. If we want to look at this accumulation function, there's nothing that stops us from simply evaluating this definite integral. I know it kind of freaks students out the first time you see this because we're used to there always being a number there instead of an x. Well, how are things different now that there's an x there? Well, it turns out, yeah, you can do a few different things, but we can still evaluate that definite integral even though there's an x there. No problem at all. Okay? In fact, that's what we're going to do. So here, I mean, of course, I have the answer here in the text, but I'm gonna kind of develop it with you, and so I'm just gonna solve it again over here in the margin. Okay, so if I want to evaluate that definite integral, and again, that's what I want to do. Basically, I want to find the explicit definition of the accumulation function. So of course, I have the accumulation function is equal to this integral, but I can find out that this function is equal to, like, I don't know, sine plus cosine or sine of 2x or something. I can figure out, that is, I can get rid of the integral notation. I can just figure out what the function equals by simply evaluating the integral. So let's see. Let me start over here. We have the definite integral from 0 to x of 4 sine. I'm going to go ahead and write this sine 2t and then square it like that because that's what sine squared means. Times cosine of 2t dt. So just keep in mind we're integrating with respect to t, and eventually we'll have to evaluate using the second fundamental theorem of calculus. We'll have to do capital F of b minus capital F of a, where capital F of b means plug in x because x is the upper limit of integration. Now, notice this is certainly composite. It's actually one of these like doubly composite situations because sine of 2t and cosine of 2t, obviously those are composite, but sine of 2t quantity squared, that's also composite. Now, I think, let's do that. Okay, so I think for our substitution, let's let u be the main, I'll call it the main inside function, which is sine 2t. Okay. Now, again, well, what do you do if you think you're right? The first thing you do is take the differential. You calculate the differential, and you get du. Okay, this requires the chain rule. So, what's the outside function? What's the inside? Let's just review the chain rule, I guess. Outside is sine t. Inside is 2t. So the chain rule says you take the derivative of the outside function, you get cosine. You immediately evaluate at the inside function, get 2t, and then you multiply by the derivative of the inside function, you get 2. And now this is a differential, so we write dt on the end because this is differential form. Now, here's what we notice. Notice we almost have du exactly. We have cosine 2t dt. We need cosine 2t times 2 dt. But watch here. We have a 4. we can split that 4 into 2 times 2 and put the 2 we need over exactly where we need it. So let's do this. Let's rewrite this as the definite integral from 0 to x of, let's leave a part of the 4 there, the 2, and then we're going to do, we need a parenthesis. We're going to do sine of 2t quantity squared, and then we're going to go cosine 2t times 2 dt, and there we go. There is exactly what we need for du. And now notice here, there's exactly what we need for u. Now, we do have this 2 right here, but how can we handle a 2? We know how to handle a 2. It's a constant. We can factor it out. Okay? So I'm going to factor that 2 out on the next line. I'm going to factor that 2 out, and then we have the definite integral, and now we're replacing sine 2t quantity squared with u squared, and then cosine 2t times 2 times dt. That is exactly what we know du is equal to. Now, the one thing we can't forget, never can forget, is that we have to adjust the limits of integration. So, what was our original substitution? It was right here. Let u equal sine 2t. Now remember, what I have to do here is I have to plug my original limits of integration into that function for t and then see what u equals. So usually I go over here and I say something like this. If t equals what? 0 is the original lower limit. So if t equals 0, then u equals sine of 2 times 0, which is sine of 0, which is what? 0. Sine of 0 is 0. Okay, so my lower limit of integration actually doesn't even change. 0 maps to 0 in our substitution, so it stays as a 0. Now, what about my upper limit? Now, I'm going to have to erase this to get a little more room here. Now, with my upper limit, I say, all right, my upper limit, if t was equal to what? Well, this is going to look weird, just bear with me. If t is equal to x, then u equals sine of what? Well, I plug in my x, and I just get sine x, or sine 2x rather. Now, it is just what it is. It's sine 2x. So this is where it's going to look weird, but just proceed with how you evaluate definite integrals. Don't let it bother you that there's going to be a sine 2x right there. I know it looks weird, but there's nothing that says we can't do that. Usually there's a number, but we can put a function there too. Okay, and now we just proceed with the fundamental theorem part 2, which says, all right, I have a nice power function. I know how to find the antiderivative. So all I got to do is find the antiderivative, then evaluate capital F of b minus capital F of a. So we have 2. And then what's the antiderivative of u squared? Well, we increase the power by 1. We get u cubed and divide by that new power. No need for a plus c because this is a definite integral. And now we need to remember our notation, which is a 0 and then a sine 2x, because this means we're about to apply the fundamental theorem. I'm going to factor out that 2/3 like so, and then I just have u cubed for my f of b minus f of a. So what? This is going to be sine 2x cubed minus 0 cubed. So that is my capital F of b, where I plugged in sine of 2x, and there is my capital F of a, where I plugged in a 0. So I used all the usual methods for applying the fundamental theorem of calculus part 2. Now, what do we have? Well, let's just clean this up a little bit. We're basically done with finding the value or the expression of g of x. We just get 2/3 and what? 2/3 times sine cubed 2x, which, by the way, that's exactly what I have there. Okay, I just wanted to explain a little bit in detail where each of those steps came from. Okay, it's always nice to hear it instead of reading it all the time. But I try not to skip any steps or anything. And when I write these examples out. Now, what was the point of that? So now we know what g of x equals. G of x equals 2 times sine 2x cubed over 3. That is what the accumulation function is equal to. My point of doing that is there's no longer an integral involved. It's just here's the function. Okay? But what I want to do now is evaluate that function at all those original x values. Okay, at those whatever 8 or 10 of them, however many there were. Okay, and I have all that arithmetic done down here. I'm not going to reinvent the wheel for the arithmetic. You can verify on your calculator that these are correct. What we're doing now. Basically, one way to think about this is that okay, if I wanted to evaluate g of 0 and then g of 3/4 pi and then g of 3/2 pi, I could do that by individually doing 3 different, in this case actually there's 9 of them here, I could individually do 9 different definite integrals and get all these answers. But why would I want to do 9 definite integrals? Because instead what you can do is you can figure out the exact definition of g, which is right there, and then just plug in all your x values. Because this, basically what it is, it's like the integral already done for us, except everything except for plugging in the upper value of the upper value the upper limit of integration. So basically, it allows us to quickly do 9 definite integrals. So when I did this work over here, I only, practically speaking, did 1 definite integral. But now I can do all of these. These are 9 different definite integrals, and I can do them very quickly by just plugging in a 0, a pi over 4, a pi over 2, a 3 pi over 4, a pi, etc., etc. So that's what one way to think about an accumulation function. That if you evaluate the definite integral one time, it allows you to quickly take care of subsequent definite integrals. So that's one way to think about it. Now, like I said, I'm not going to reinvent this wheel here. You can check my trig. You can check using your calculator. But you do see an interesting pattern here. You get 0, 2/3, 0, negative 2/3, 0. So like you're bouncing back and forth between positive 2/3 and negative 2/3, with 0 in between. Okay. Now these are the values of g of x. Now what I want to do, just like I did in the previous example, is plot all these. So imagine again, you get a t-chart, okay, where you have x and g of x. Okay, where you have 0, I'm not going to do all these, but you have like 0, pi over 4. Well, what we find? We found 0, g of 0 was 0. So the y value is 0. What was the y value of pi over 4? 2/3. What was the y value when you plugged in a pi over 2? Well, pi over 2 is 0. So imagine I do that for all 9 values, but even more than that, I do that for all real numbers, which of course, a computer will do that for you. That's what graphing software does for you, essentially. Okay, so I do that for all real numbers, and what I get is this graph. By the way, here's a graphical representation of each of those accumulation functions, or each of those accumulation values. And here, just to drive the point home, that is equal to the definite integral from 0 to pi over 4 of, whatever it was. Okay, this was the definite integral from a 0 to 5 pi over 4, of that big function. Actually, it was a dt. I'm not going to dx there, just out of habit. So you can see how basically we certainly did evaluate 9 different. Here's 0 to pi over 2. of whatever dt. And here is 0 to 3 pi over 2 of whatever dt. We just did 9 different definite integrals, and here's the graphical representation of those 9 definite integrals. Okay, showing you how we are accumulating area. So here, I broke it up according to x-intercepts. So here, we accumulated 2/3 positive, but then on the next go around, okay, we had 2/3 positive, but then we have the exact same region under the x-axis. So we have 2/3 positive, 2/3 negative. They sum to 0. And then when we go to 3/4 pi, well, then we have 2 regions underneath the x-axis that both have area, a net area of negative 2/3, and we have 1 above the x-axis. So that sums to, there's 2 below, 1 above, so you get a negative answer, you get negative 2/3. And then you see how, we keep accumulating area, we're working from left to right. Each time we're incorporating another one of those either peaks or valleys, and that's where the expression, that's where like that table of values would come from. And by the way, that table of values leads to this picture. If you watch, if you g of pi over 4 equals 2/3, that means that pi over 4 has a y value of 2/3. That y value right there is 2/3. All right, g of pi over 2 means you have a y value of 0. Or g of pi over 2 equals 0 means you have a y value of 0. So notice these x and y value pairs are making up this graph. That means pi comma 0, this right here, means pi comma 0 should be on my graph down here. And it is. Pi comma 0. Okay, so g of x came from all of those calculations. Now, here's the observation that I wanted you to make from, we talked about this in the last video. Here's the neat, interesting observation we need to make about accumulation functions. Okay, notice that the slope, like here in this paragraph, that I have written out here, the slope of g at x equals c is f of c. So, I wrote this on the last video, that g prime of c equals f of c. That is, if you want the slope of this function, this function is g. If you want the slope of that function at some value of c, all you have to do is plug back into the original integrand. Now, what was the original integrand? It's on the last page. It was a big long function. Oh, it was this. That was the original integrand. 4 sine squared 2t times cosine 2t. So let me jot it down here. Where f of t equals those 4 sine 2t squared cosine 2t. I think that's correct. Okay? For instance, let's see if that works. Well, let's see. If you want the slope at pi over 2, what do you imagine the slope is right there? Looks to me like it's horizontal. So if you plug pi over 2 into that expression, you should get 0, because we know that g prime of pi over 2 is 0. That means that f of pi over 2 should also be 0. And I think that makes sense, right? Because if you plug in pi over 2, you get sine of 2 times pi over 2. That's sine of pi. Sine of pi is 0. 0 squared is 0. 0 times 4 is 0. 0 times cosine of 2 pi is 0, because this whole thing zeroes out if any one of those factors is 0. So yes, and that is the major observation, is that if you want a slope on the graph of your accumulation function, and this is the accumulation function, all you have to do is look at the y values, the function values of the integrand. Here, I typed this out on Desmos, and let's look at it side by side. So here, this red function is the original. It's the 4 times sine 2t squared times cosine 2t. Here's the accumulation function. So what the major link that you need to see is that if you want the slope on the accumulation function, that is like the slope, say like I said, pi over 2. Or let's say right there. What's the slope right there? It's a peak, has a slope of 0. Oh, I lost Desmos. Let's see here. Where'd you go, Desmos? There you go. So notice the slope right here at pi over 4, it should be 0 because that's a relative maximum. Notice the y value of 0 on the original function, f of t. If you want, say, the slope at pi, so notice pi has a horizontal tangent line at pi on this is the accumulation function. Notice that pi is a x-intercept on the original function, on the integrand. So that is the interesting link here, is that the slope on the accumulation function is given by the y value on the original function. That's the kind of a cool thing. Now, here's the thing. We can actually verify that with differentiation, with derivatives. And here's the work to show it. So when I say that g prime of c equals f of c, that means that when I take the derivative, I should get the function f. That is, I should get that function. Let's see. Here's a couple of our old rules from our differentiation days. If you want to take the derivative of g of x, so there's g of x. If you want to take its derivative, well, let's first of all, hopefully if I've taught you anything, it's that you don't need the quotient rule when you're dividing by 3 a constant. So let's factor out, in fact, let's do more than just factor a 3 out. Let's factor a 2/3 out. So we can factor a 2/3 as a constant multiple. We can put it right there. And then we just have to apply the chain rule. Okay, if we apply the chain rule here, let's say outside function, inside function. The outside function is x cubed. The inside function is sine 2x. So we apply the chain rule, which says, hey, you differentiate x cubed, you get 3 times something squared. Then the chain rule says you evaluate at the inside function, you plug it in, and then you multiply by the derivative of the inside function. Well, lo and behold, guess what? The derivative of the inside function, that's also composite. So we have to use the chain rule to take the derivative there. So what's the outside function? Well, the outside function is sine x. What's the inside function? 2x. So apply the chain rule all over again, and that's where we get, hey, eraser, work. Okay, there we go. That's where we get this business right here. Because the derivative of the outside function, sine, is cosine. We evaluate at 2x, and then multiply by the derivative of 2. And of course, the derivative of 2 gives us, of 2x gives us 2. And what do we get in the very end? We get this, and then we simplify, and notice that we get the original function back. We get the original function back. So there is a very interesting link. And again, it's this link that I have boxed up here. That if you want the slope, i.e. the derivative of the accumulation function, the integrand gives that to you. And I might not have convinced you that's really interesting. I hope that I have, using these graphs and such between this example and the last example. But that link basically between, and I guess here's why the link's so important, because think about it. Let me go back to maybe the original statement. We're saying that the slope of g is equal to the integrand right there. So the slope of g is equal to the integrand. In other words, there's this linkage between slope, i.e. derivative, and integration, a definite integral and such. So we'll explore that in more detail in the next video, because that's hinting at exactly what the first fundamental theorem of calculus is telling us. So the first fundamental theorem of calculus is gonna talk about the linkage between differentiation and definite integration. There's this very interesting concept, theorem, called the first fundamental theorem of calculus that links those two concepts. And that's where we're headed in the next video. The purpose of this video was just to get you more exposure with accumulation functions. You'll have a bunch of homework questions about accumulation functions. Yeah, don't let them confuse you. Just you're accumulating area as you work your way from left to right. From left to right, now it's accumulating net area from left to right. And we've talked about a couple key observations that we should make about such functions. All right, as always, feel free to reach out. Always more than happy to help you. And here is your periodic reminder to be putting in a couple hours a day, especially towards the end of the semester. This stuff gets super deep, super hard, and you'll drown in the information. It's just too much if you're not putting in the couple hours that's required each day. Don't think I'm crazy. I might be crazy, but the time you need to spend is on the order of a couple hours a day, even for the quote-unquote top students. A couple hours a day is what's required. Okay, and as always, I'm here to help you. The tutoring centers are here to help you. The math lab is here to help you. We have lots of resources here for you. All right, I'll talk to you in the next video.